lecture 21 now, we're going to get started talking about capacitors. So in the previous lectures, we finished up talking about electric potential and electric potential energy, and now we'll move on to a new chapter, which is chapter 24. Chapter 24 is all about capacitors. Capacitors are devices which are used to store electric potential energy. So if you look inside a piece of electrical equipment, you'll see, some sort of circuit board that looks like this. These pieces here, these are the capacitors, and what capacitors do is they store electric potential energy. We use them in all kinds of circuits, so we're going to study these as circuit devices. Okay, so let's get going on how we talk about capacitors. So we did discuss capacitors when we discussed electric fields, and as a reminder, a capacitor is two conducting plates. They each have an area A. They're separated by some small distance d. And when we say the plate separation is small, we mean compared to the dimensions of the capacitor plates itself. Each plate has the same size of charge, but its opposite sign, and it's very useful to know the surface area charge density Q, which has a symbol of sigma. That's the charge divided by the surface area. It has units of coulombs per meters squared. So when we use capacitor in circuits, we're going to be drawing circuit diagrams. So in a circuit diagram, we'll have ideal wires. So a straight line like that is a wire. And they'll go into a capacitor. So this is an ideal wire. Ideal means it doesn't have any resistance. It doesn't use up any energy. And these two short parallel lines, that's a capacitor. And then we'll use another piece of ideal wire to go to our next circuit device. When we talked about this in terms of electric fields, we found that the electric field outside of a capacitor was 0, and the electric field in between the plates was sigma over epsilon naught, and that pointed from the positive plate to the negative plate. So that's something we knew from our previous chapter. Capacitors, when you buy them from the factory, they come completely uncharged, so no charge stored on the plates at all. How do we charge up a capacitor? Well, we connect it to a battery in a circuit. So if we asked how to charge the capacitor, so to charge it, we connect it to a battery or a power supply. When we did that, our circuit diagram would have a capacitor in it, C for capacitor, and it would be connected to a battery. Batteries have one long line, one short line. The long line is the positive terminal, the short line is the negative. So this symbol is our battery. Batteries are classified by their potential, which has a symbol of delta V or epsilon. So we're going to be drawing a bunch of these circuit diagrams as we go through the chapter. Okay, let's go through the details of charging a capacitor. So exactly how does that work? So let's think about what happens inside a battery. The way a battery works is it's full of some sort of chemicals inside, so battery acid inside. Inside the battery, we get a chemical reaction. That chemical reaction inside the battery makes positive charges move towards the positive terminal. So we get a positive charge inside the battery, and because of the chemical reaction doing work on that positive charge, it will move towards the positive terminal. So that's what happens there. It hits the positive terminal, and then it goes out of the positive terminal, and it flows along the wire. Keeps going along the wire. This is our ideal wire, and then it comes and it hits the top plate of the capacitor. In between these two capacitor plates, for now anyway, we just have empty space. So when the charge gets to here, it has to stop. So the charge hits right here, and then what happens right here? Well, this plate up here has one more positive charge than this plate down here. What's going to happen then is a positive charge from this plate is going to be pushed away. So up here right now, this plate has 3 positives. So it's going to make a positive leave to balance out the charges. So that's going to leave, it's going to come around the circuit until it flows back into the negative end of the battery. That cycle is going to continue. It's going to happen over and over and over, and it will continue until the potential difference across the plates of the capacitor equals the potential difference of the battery. So the charge will flow from the battery to the capacitor until delta V of the battery or the power supply equals delta V of the capacitor. And our diagram here is the circuit diagram equivalent of what's happening here. We've got our battery. The charge is flowing out of the battery and around the circuit. A positive will hit here, will repel a positive from here, and it will flow around. C here for capacitor. Okay, one thing we might note here is that this flow of charge, that's what we call current. This whole process happens really fast, so it doesn't take very long. It's something we can measure, but it does happen quite quickly. Once we get our capacitor fully charged up, then we disconnect the circuit and we have a fully charged capacitor, which we can now use in a circuit device. Okay, so that's how we get it charged in the first place. So now let's ask, how do we talk about capacitors? So we know that batteries are characterized by their potentials. Turns out capacitors are characterized by their capacitance. Capacitance has a symbol of the letter C. The units are called farads. And farad has a symbol of a capital F. Okay, so if a capacitor is characterized by the capacitance, how do we figure out what capacitance is equal to? So let's think about a capacitor where we have 2 plates with equal and opposite charge. So positive charge over here on this plate, negative charge over here on this plate. We know that our plates are separated by some small distance d. And we know that there is an electric field maintained between the plates. That's drawn in our picture here. And we also know that there is a potential difference between the plates. We know that the size of the electric field is sigma over epsilon naught. We know it points from positive towards negative. Just as a reminder, sigma is the charge density, which is the charge divided by the area of the plate. Okay, so let's start with this idea of the magnitude of the electric field, sigma over epsilon naught. And let's fill in that sigma is charge over area. So E is sigma over epsilon naught, or Q over epsilon naught times A. So Q over A is sigma. What else do we know about electric field? So we'll say and the potential difference between the plates of a capacitor, we studied this in the last chapter, that's the magnitude of the electric field times the plate separation. Let's try and put these two things together. Maybe I'll switch colors of my pen here. So delta V equals E times D, but E is Q over epsilon naught times A, so we'll sub that in. Now let's rearrange and we'll solve for Q. So Q is equal to A times epsilon naught over D times delta V. Okay, this is a good report, good result. This is pretty interesting. What we see is that Q is proportional to the potential across the plates. So the charge on a plate is proportional to the potential difference between the plates. And the constant of proportionality is this number right here, and we call this C. Okay, so let's get this down. So Q is proportional to delta V, constant of proportionality. Is capacitance C, which is A epsilon naught over D. So an equation we're going to use quite a bit is that C equals Q over delta V. Let's put that one in a box. And C is A epsilon naught over D. So here capacitance is the amount of charge divided by the potential difference between the plates. Because C is A epsilon naught over D, it shows that C is a material property of the capacitor, or a device property. It depends on the size of the capacitor and the separation between the plates. Let's see, what else can we say about our units? We said that the units were farads, so capacitance is farads. We see that a farad is a coulomb per volt. And we know that a volt is a joule per coulomb, so a farad is coulombs squared per joule. So this shows us that capacitance is related to energy and energy storage. Okay, so that talks about our capacitance, which is how we classify a capacitor. This is an interesting fact here that it depends on the plate separation. So an interesting application of this is that sometimes this plate separation could actually be variable, and if D changed, the capacitance would change. And that's actually how, musicians might know this already, that's how a condenser microphone works. So this is a lady singing into a microphone. In our condenser microphone, there are two plates in the microphone. One is rigid, it's held in place, and the other is flexible, and it's held at constant potential. The sound waves coming from her mouth make the flexible plate vibrate, so that moves back and forth. As it moves back and forth, the plate separation changes because it gets closer and further apart. That changes the capacitance. If the capacitance changes, but the potential is the same, the charge will change. So right here, we hold the plates at a fixed potential. We change D, so we change C, which means we change Q. Okay, let's put that together. She sings, it flexes the plate. Flexing the plate changes the capacitance, which changes the charge. Charge is flowing in and out. That charge flowing in and out, that's current. So current gets measured by an ammeter, so her singing, that sound gets converted to an electric signal that can then be amplified or digitally recorded or something. So that's something cool that maybe the musicians knew or would be interested about. So maybe that's something for the musical people to like. Okay, let's do a conceptual example. So let's think, if we have a capacitor with just empty space between the two plates, if we double the charge on the capacitor, what happens to the capacitance? Okay, so we have three choices. I'm going to say, why don't you hit pause on the video, you think about what your answer is, then really commit to it, and then come back and hit unpause, and we'll see what the answer is. Okay, now that you've unpaused, let's see what the answer is. Maybe I won't say the answer first. Let's think about the equation for capacitance. C equals A epsilon naught over D. Here we are doubling the charge. This doesn't depend on charge. So if we change Q, whoops, I meant to say change and I wrote charge. Change Q, we don't change the capacitance C. So that tells us that the answer here is number 3, no change in capacitance. So it doesn't increase or decrease, it doesn't depend on the size and shape, it stays the same. Okay, what's another way we could think about this if we wanted to? So if you're not satisfied with this equation, let's think that our first capacitor, C1, has charge Q1, and the potential between the plates is delta V1. So this is the first capacitor. Our second capacitor, Q2, would have charge twice Q1, so we've doubled the charge. Let's ask, what's our new capacitance? C2 equals. So C2 is going to be charge Q2 over delta V2. Q2 is twice Q1. But what's delta V2? So we've doubled the charge. What happens to the potential? Well, delta V2 is E2 times D. E2 is sigma 2 over epsilon naught. That's times D. Sigma is charge over area. Q2 over area times epsilon naught times D. Q2 is twice Q1 over A times epsilon naught times D. Q1 over area is sigma 1. Sigma 1 D over epsilon naught. Sigma 1 over epsilon naught is E1. E1 times D is V1. So we see if we double the charge, we actually double the potential as well. Okay, so that's 2Q1 over 2 times delta V1 equals Q1 over delta V1 equals C1, no change. Okay, as is frequently the way in physics, there are different ways to get at the same correct answer.